Okay, this is 5.4, solving rational equations. The goal today is to connect the solution to a rational equation with the graph of a rational function. The first question is really the only difficult one. Okay, so if you're gonna pay attention, now would be the time. This is the only one that really will probably confuse you guys come the test. So it says when they work together, Stuart and Lucy can deliver flyers to all homes in the neighborhood in 42 minutes. When Lucy works alone, she can finish the deliveries in 13 minutes, less time than Stuart can when he works alone. Okay? So this is actually quite a difficult question to set up, I'll be honest with you. Without looking directly at the solution, can anybody have any ideas of where you might want to start? Because if we just go through the solution, it's going to seem like it's easy and make sense, but you know, if you just read this and try and start, it's actually quite difficult. So I want to give you guys a little bit of a taste of that before we just go straight to the solution. Where would we start with this? Obviously, I hope most of you recognize we need to introduce some variables, right? We want to use algebra. We're not going to be able to graph this right away. Yeah.
There would be time, so
There'd be what?
42 and 13 would be x.
42. Okay. Yeah. So if you're thinking of it like a graph, you're putting time over here, and then you put number of hours worked. Okay. Okay, that's good. That's one way to think of it. But typically we wouldn't start with a graph. We'd kind of start by creating variables, right, for this question. Elijah, yeah.
You can make a variable for the amount of time that Stuart takes, so it would be the time that Lucy takes plus 13.
Very good, yeah. So that's the idea, right? The question is asking, when Lucy works alone, sorry, here's the question. When Stuart works alone, how long does it take to deliver the flyers? So we're really trying to figure out how long it's going to take Stuart to deliver the flyers. We know it takes Lucy 13 minutes less time than Stuart. So why don't we, if we're looking for that particular variable of Stuart, what can we assign to the number of hours it takes Stuart to deliver the flyers when he works alone? What variable would we want to use for that? Yeah. Yeah, maybe S, right? So we'd say let S equal the number of hours Stuart takes to deliver the flyers. So this is what we're trying to find now. We're trying to find S. That's the goal. We have some other information now, right? We know that Lucy, when she works with them, combined they take 42 minutes. And it also, when Lucy works alone, she takes 13 minutes left. So what variable do we want to assign for Lucy's amount of work? Yeah, L, obviously, right? So L is going to be equal to what? Marco in the back.
Time it takes for Lucy to deliver the flyers?
Yeah, so, right. Well, what would that be equal to in kind of reference to our other variable?
S minus 13.
Good, very good, yeah. So this process here that we just did, this is arguably the hardest part. Okay, just setting up that. I know it seemed easy, but it's not really. When you go from when you're staring at a blank page and you're trying to get these variables, you know, this process, and it's hard to teach from a teacher's perspective. There's not much more I can tell you than, yeah, you know, this makes a lot of sense to do this, but I want to give you kind of a taste of that, and that's why we went through that process. So these two variables make sense. Now, I said this is the hardest part. It's not actually. We got to set up an equation with these two variables and somehow involve this 42 minutes, right? Because it's our last piece of information. So anybody want to take a guess of what we can do for that? Yeah, Lyndon.
S minus 13 bracket.
Sorry, I can't hear you.
Oh, sorry. Bracket S minus 13. Close bracket. L plus 13.
Okay. Okay, a valid attempt, right? He's tried to set it up. He's involved at least one of the variables that we created. You wouldn't want to introduce L, right? Because we've already, you know, essentially substituted out L. And we want to have as little variables as we can. So definitely we wouldn't have put L here. Another problem is you're taking Stuart's hours and you're multiplying it by Lucy's hours, I don't know why that won't give us a value that makes any sense, right? Their hours multiplied. So not the best. Anybody else want to give it a shot? It's not easy, right? You have to come up with a way to relate the amount of hours that they're working to 42 minutes, right? Because that's what we know. Remember, if we go back to the original question, it says they can deliver the flyers to all the homes in the neighborhood in 42 minutes. Yeah, Joseph. No? Okay, so what I would kind of expect you guys, this is what I was kind of fishing for. I was fishing for this. And maybe you guys thought about it and thought this probably isn't, I don't know if you thought that it wasn't the right answer, if you were just too shy to say anything. But it's tempting to do this, okay? And this is what naturally I would have thought, you're taking Stuart's hours and you're adding Lucy's hours, and together they take 42 minutes. But the problem with this is now you're adding their hours. So you're gonna take longer. So you're adding the amount of time it takes Stuart to do it by himself, and you're adding the amount of time it takes Lucy to do it by herself, and you're trying to equate that to the time it takes both of them to deliver the flyer. So there's something wrong with that, right? You guys understand that?
Yeah, that makes sense in my head. Like, you're taking Stuart hours, adding it to Lucy's hours. Wouldn't that combine both their hours?
Yeah, but when they're working together, they're gonna get finished a lot faster than if they were working individually. Right, so it takes Stuart S amount of hours to do it all by himself. So already that's gonna be more than 42. So if I add those hours to Lucy's hours, it's gonna be even more than 42. So it makes no sense, this current equation. So what we need to do then is we need to establish kind of a unit rate at which the amount of time it takes them to deliver one flyer by themselves. Does that make sense? Because then we can equate the rates at which they deliver flyers. Does it make sense? So Stuart delivers at a certain rate. He's doing so many flyers, let's say, per minute. If we can get his rate per flyers per minute and her rate flyers per minute, then we can figure out how much their rate is together, which is 42. Does that make sense?
Yeah.
Okay? That's what these questions are all like. They're all like this, rates, okay? And the pattern is the same. But it's important, I wanted to explain it before I just show you the equation, because you're gonna look at it and be like, oh, that's kind of strange, but that's where it came from, okay? So here it is. It's close to what we had. 1 over s plus 1 over s minus 13 is equal to 1 over 42. And here's the explanation, okay? So the fraction of deliveries made in 1 minute. So when Stuart works alone, he makes 1 over s deliveries in a minute, because s is the total time he takes to make all deliveries, right? So let's say Stuart takes 50 minutes to make all deliveries. How much is it going to take him to make one delivery? 1 over 50. Does that make sense? His 2 deliveries is going to take him 2 over 50. 50 deliveries is going to take him 50 over 50 to make 50 deliveries. Okay, so that's where the 1 over s comes from. Does that make sense now? Okay, so if that makes sense, and then Lucy's working alone, it takes 1 over s minus 13, which makes sense because we've already established that as our variable for Lucy up here. So now we're adding the rate at which Stuart is delivering plus the rate at which Lucy's delivering in 1 minute is going to equal to their total combined time, 1 minute of their 42 minutes. You guys get it? So if I add the rate at which Stuart delivers in 1 minute plus Lucy's 1 minute, it's going to equal their combined time of 1 of 42 minutes. Okay? So it might be even tempting to say, well, this is kind of the same as this. It's very, it's very, sorry, not this one, this one. It's very different, okay? You can't just take the reciprocal of each one of these and say that they equate the same, right? It doesn't work that way, okay? So here's your equation. So very important how we develop that. Once we have that, that's the hard part. The hard part's done. The rest is just kind of algebra and moving the numbers around, reverse operations and solving. Any questions about that? I know it took a long time, but it was important that we went through that process. So now when you see another question like that, your mind starts thinking, well, I can't just add the variables. I got to, determine sort of a rate. Yeah.
So every time it'll be like a different equation?
Yes. Every question will be a different equation. Okay. So here, just to kind of give you guys a visual, in brackets is what we started with, right? All of these problems that we're going to cover today in 5.4, the strategy is the same. Because there's nothing immediately in common between the denominators, you just multiply by the product of all the denominators. Okay, so we can cancel out the denominators. So when I say the product of all the denominators, I'm talking about, here's our denominators, s minus 13, and 42. You're going to multiply both sides on the numerator by all of those denominators multiplied. So that's where this 42s minus 13 comes from. And what that allows us to do is it allows us to take everything out of the denominators so that we're moving everything up. Okay? So here we multiply by here. The s is going to cross out here, so we're left with 42s minus 13 over s plus this value now times here. So it's times 1, so that stays on top, over s minus 13. The s minus 13s are going to cross out in the next step. Do you see that? And then the 42 is crossed out here. So we're left with this equation. And that process is the same for all of the quotient equality equations that we're dealing with today. Any questions there? All right. So once we have that, we expand and simplify, move everything over. We're left with this. If you're very good at factor by inspection, you can do the multiples and figure out this, or you could have just went using the quadratic equation. Okay? Some big numbers. Your C value would have been 546, but in any event, this shouldn't be too difficult for you guys now, right? We're much beyond that. It's at the very end of the question. Okay, and we get two answers. We get 6 or 91. It's important now to go back to the original question and evaluate these responses. Can S be 6? If S is 6, if we go back to our original variables that we created, if S is 6 here, we're going to get -7 for Lucy's hours. So that can't happen, right? It can't take Lucy, less than 0 hours to deliver all the flyers. So this value then is inadmissible. Any questions there? Okay, so the only answer then is 91. So S is 91. Lucy, you just subtract 13 from 91. Okay? Now the next solution, I'm not going to focus too much on this because they use a graphing calculator, but it's important to understand the similarities, okay? Because if you're given a graph, you need to know what they're going to be. When we graph this function here, basically our zeros are going to be Stewart's number of hours, right? Because we're solving for S when it equals 0. So you'll see that we get, again, 6 and 91 is way over here. Okay, so we get the same answers by just punching that formula into a graphing calculator and setting it equal to 0. Okay, why do we set it equal to 0? Because that is where our graph meets the x-axis, and that would be our value of S. Okay, from the original equation that we created. All right, the other questions are quite a bit easier, I have to admit. That's the hard one. All right, solve each rational equation. X minus 2 over x minus 3. Whenever we have this scenario, remember we can multiply both sides by x minus 3 to cross out that x minus 3. 0 times anything is still 0. So we have x minus 2 is equal to 0. So therefore, x is equal to 2. Okay, very simple. It's important to state, however, that in this case, x cannot equal 3. I'm not sure why they didn't mention that here. Okay, and you can actually see that in the graph that x equals 3 is a vertical asymptote. Okay, and we know that from the last section, we would have had 1 over 0. A number over 0 is a vertical asymptote. Okay, so it's important to call out and get in the habit of calling out these restrictions before you even start the problem. So here we would say x cannot equal 4, x cannot equal -2. Okay, that's because both of these denominators would have a 0 if they did. Any questions there? Okay, so now with this example here, what we can do is we can multiply both sides by the product of the denominators. So x minus 4 and x plus 2. And what that allows us to do then is cross out on this side the x plus 2 and cross out on this side the x minus 4. Okay? And you'll see that on the next page. So here we're multiplying both sides by the product of the denominators. We're crossing out the common factor. We're left with an equation that we need to expand and simplify here. This actually simplifies directly into one value of x because our x squares subtract out. Okay, so that's nice and easy. We get x equals -0.2. And then if this was a word problem, I would look at this value and go back and say, does it make any sense in relation to the word problem? You know, that's always a good practice. You should always be thinking about your final answer and how does it relate back to the original question. All right, example 3, connecting the solution to a problem with zeros of a rational function. Okay, again, so here's our given equation. We're told it's called the concentration of salt, C, over a period of time t. So again here we can say you know, t cannot equal -25. Actually it cannot be less than 0, right? Because you can't have a time that's less than 0. So it's important to state those restrictions again even before you start the question. When does the salt concentration in the tank reach 3.75 grams per liter? So Luke, what would I do with that value? 3.75. To where? For what?
What is the salt concentration?
Yeah, so for which variable?
Plug it into the overall because you're solving for the time, which is the x.
Yeah, you plug it in for C, right? The concentration.
Yeah.
Right here.
The y or the c.
Yeah, the Y, yeah. Okay. Multiply both sides again by the denominator, the product of the denominator. In this case, there's only one denominator, so I'd multiply by 25 plus t. Okay, these cross out, and this is 25 plus t on this side. Okay, so we do that here. These cross out. We're left with 10t is equal to 93.75 plus 3.75t. And again, it works out where there's just a t variable. We can solve for t directly. We get t equals 15. Okay? So the salt concentration is 3.75 after 15 minutes. Any questions there? Alright, finally, last one. Example 4, using a rational function to model and solve a problem. Alright, so another interesting one. This is similar, closer to problem 1. Not quite as difficult, but still, you need to come up with these variable values. So Luigi, can you read example 4 and try and come up with the first variable?
Rima bought a case of concrete t-shirts for $450. She kept two t-shirts for herself and sold the rest for $560, making a profit of $10 on each t-shirt. How many t-shirts were in the case?
Okay, so what do you think? Where would you start?
$450 over X. You put the.
You're reading the solution?
Yeah.
Try and think about it without looking at the solution. Okay, because that's the way you're going to learn, right? So put the solution away. So let's think about it. She bought for $450 a case. She kept 2 and she sold the rest for $560. She makes a $10 profit on each t-shirt. So we want to make an equation where we can say how much she bought for, how much she paid for a shirt minus how much she sold for a shirt is equal to 10, right? Sorry, how much she sold a shirt for minus how much she paid, because there's a profit of 10, right? Does that make sense?
Yeah.